Hi, everyone, and welcome to the machine learning class. So in this small video, we're going to discuss a little bit of the introduction about machine learning. And we're going to also see the definition of machine learning, various types of machine learning algorithms, including supervised and unsupervised learning, as well as a few more examples of basic algorithms that are important. So machine learning is everywhere. We have applications that involve image recognition, security applications, autonomous vehicles, personal assistants such as Google Home, Alexa, recommendation systems that are being implemented through our Amazon accounts and Netflix accounts. So machine learning is actually in our lives. So what is machine learning? It used to be the case that we used computers for which we prescribed specific instructions, and by prescribing those instructions, we were able to have computers automate our tasks. Now, due to the emergence of a lot of data, it's not only possible to define the tasks for the computers, but it's also very possible for a computer to learn how to perform a task using the patterns in the data that the computer has seen. So essentially, what machine learning does is that it helps the computer learn patterns of data, and then the computer actually decides based on the data that it has been provided. So one of the important advancements that have led to the emergence of machine learning are the large amounts of data that are being created every day. For example, we have 40 billion web pages, hundreds of hours of YouTube videos that are uploaded every minute, millions of transactions that are being performed per hour. So all this data contain valuable information that can be used in various decision-making tasks. And our computer can actually process the data, analyze them, find patterns, and through those patterns can provide decisions. A possible definition of machine learning that has been given by Dr. Murphy is that machine learning comprises the set of methods that can automatically detect patterns in data and then can use those methods to predict future data or perform other kinds of decision-making tasks under uncertainty. So essentially, this taps into the idea of what we have said, that we need some data, we need to find different patterns from our data, and based on those patterns, we can actually predict future patterns in data that we haven't seen. A more formal definition of machine learning is a computer program that learns from experience E with respect to some task T and with some performance measure P. So the computer learns if the performance on task T improves with experience E as the performance is measured by measure P. So this is a little bit more formal and more theoretical definition. However, here we have an example of how this definition can be actually exemplified. So in this example, suppose that your Facebook account watches the users that are added to your friends list. And based on that, your Facebook account learns how to suggest new friends for you. What is the task T in this setting? What is the experience? And what is the performance measure? So we understand that essentially, since our Facebook account learns from the data, the experience would be what friend requests we have gotten or what friend requests we have actually extended through Facebook. This would be the experience, the data that our algorithm would learn. The task now could be something like a task of classifying whether a user is good to be our friend is whether a user is likely to be on our friend request or not. And of course, the performance is how accurate the algorithm would be in suggesting users. So if we were to actually answer this multiple choice question, we would have our task T, as you can see here, on whether a user would possibly send or not a friend request to a user X. The experience E would be basically data from all the characteristics of users to which we have extended a friend request. And then the performance measure would be whether our algorithm, whether our previous experience does well in suggesting a friend request. So essentially the percentage of suggested users to whom we have actually sent a friend request. Now, as you have probably understood so far, we have three main ingredients for any machine learning task. We have data, which is the experience that we have discussed so far, and these are collected from past observations. In the example of Facebook, this would be the data and the characteristics of the users to whom we have extended friend requests. The second key ingredient in any machine learning task is the model. So after we have some data, we have to provide some type of structure in our data. We have to actually translate these numbers into some mathematical formulas. These are the models that we design, essentially how we represent our data. The models can have various different aspects. They can be deterministic, they can be probabilistic, they can learn from our data through different ways, but they all have in common the fact that they are trying to capture, represent some type of structure from our data, some type of patterns from our data. And finally, the third component of machine learning is the prediction component, which refers to the decision-making that is performed based on the model that has been learned from our data. The decision-making is being performed on data that have not been seen by the model. Therefore, it's being performed in an unknown set of data, because this is usually what we are interested in. We are having a decision-making task, and we really do not know the decision, and we are expecting from our machine learning algorithm to provide us with its own estimate based on the data and on the experience that it has already gained. So if we were to actually describe those in an example of temperatures and predicting temperatures over the next 20 to 30 years, we can see here the graph that represents global temperatures, and with the blue points in the blue dots in the graph, you can see the average annual temperature from 1860 up to 2000. The red line is the line that represents the 5-year average. And what you can see here is that you can see overall increasing trends. So we can see that overall temperatures are increasing on average over these 140 years. And you can also see some local oscillations. So the question here is how we can design a machine learning algorithm that can learn some of these patterns from our data. And again, the data here, what we refer to as data, are the 140 blue circles, blue dots, that represent the annual average temperature for every year from 1860 all the way to 2000. So now, since we have our 140 points, we actually need some type of mathematical formula in order to represent the patterns that are depicted in these 140 points. One potential way to do this is through a polynomial line. So you can see in this blue line in this graph, some type of second order or third order polynomial line that represents this increase. And essentially it also represents that this increase is not linear, but is some type of second order polynomial increase. How we can actually learn the line from our data. Essentially, we will do what we will learn as part of the next lectures of our class. We will do some type of regression in order to fit the best blue line that optimally represents the blue dots that have been seen in the previous graph. Instead of having this polynomial line, we could have higher order polynomial lines, such as a 10th order polynomial line that potentially could have been represented by the red line that depicts a lot of oscillations on the same graph. Or we could have actually used a simpler model that only is a linear model and is being represented by just an increasing line. So these are all essentially choices that need to be made during the design of the machine learning algorithm. Through this example, we understand that there is a trade-off usually by how precise our model is on the training data and how much it can be generalized on the test data. So we can see, for example, that the blue line, which is this quadratic polynomial increase, it could be good enough in capturing the general trends, these increasing trends, but definitely it's not as accurate in capturing the local oscillations. On the other hand, the red line that corresponds to a higher order polynomial might be very good in capturing these local oscillations, but it might not be good in predicting future data, just because it might not have enough data to actually predict these local oscillations in the future. In contrast, the blue line, just because it's simpler, it doesn't require so much data in order to be estimated, it will most probably be more accurate for future samples. So we have seen so far the samples, our data, which is the first ingredient of the machine learning. We have seen the model. We have seen different types of models, from quadratic to higher order regression to higher order polynomial. We can also now see the third component of the machine learning, which refers to the prediction. So if you see this graph, we have plotted data beyond the year 2000, from 2000 all the way to 2010. And these are the data that correspond to our prediction data. So this means that we had used the data from 1860 all the way to 2000 to estimate our models, to train our models. And then this data is this model now is being captured by this black line, this black quadratic order polynomial line. Our data in this graph is being captured by each of these red dots. And then the projection of the data is being captured by the part of this quadratic polynomial line that spans between 2000 and 2010. We see that the model is good enough in predicting some of the annual temperatures. So we can see that the model actually captures the increase in temperatures that has been observed between years 2000 and 2010. However, because this is a fairly simple model, it cannot capture the very fine-grained oscillation patterns that can be seen throughout these 10 years. However, it's close enough. I mean, we could argue that if we were not so interested in these local oscillations, at least the model is close enough in capturing the increase in predicted temperatures over the next 10 years. So another way to look at machine learning is to look at 3 different components of learning. And for each algorithm that we're going to study throughout the semester, we will actually check these 3 components of learning. The first component is the representation. So representation refers to the formal language based on which we represent our model, essentially the mathematical formulation that we give to our model. If we, in the case of temperature prediction, this was the nonlinear regression line that we saw, either a quadratic polynomial line or a higher order polynomial line. That was the representation of our model. The second component is the evaluation of our model, and the evaluation refers to the function that assesses the performance of our model or the performance of our learner. Depending on the algorithm that we're using, we have evaluation metrics that actually match this algorithm best. So in the example that we saw, the evaluation metric would be the error between the predicted and actual values of temperatures, because this is what makes sense in this regression problem. If we have, let's say, a classification problem, then the corresponding evaluation metric would be accuracy, error rate, or likelihood. And these are some of the things that we are going to see throughout the class. So finally, the third component of learning refers to the type of optimization that is being approached in order to learn the representation of our algorithm from the data that we have. The optimization can actually have many different forms and shapes. We can have a combinatorial optimization, for example, a greedy search. We can have constrained or unconstrained continuous optimizations, such as gradient descent and linear programming, which are parts that we are going to see in linear regression algorithms, logistic regression algorithms, as well as in support vector machines, and of course, neural networks. So these three components of learning are always part of any machine learning algorithm. The representation, again, refers to the main structure of the algorithm. The evaluation refers to the function that assesses the performance of the algorithm, and the optimization refers to the way the algorithm learns from the data. If we were to have another categorization of machine learning algorithms, that is actually a categorization that most of the people have probably heard by now, is three types of learning: supervised learning, unsupervised, and reinforcement learning. Supervised learning refers to a task that learns a mapping between inputs and outputs. And as inputs, we can have, for example, any characteristics that might be relevant to the learning task. As outputs, we can have any outputs, any target labels that we would like to learn. A very typical example would be, let's say, the example of facial recognition. Our inputs are the images, our outputs are the different people that we would like to be able to recognize. So given that we have this set of pairs of inputs and outputs, a supervised machine learning algorithm learns to map between those inputs and those outputs. Essentially, it learns the association between these two. The supervised learning tasks are of the most commonly used. Many of the algorithms that we are going to see in this class, including all the regression algorithms that we are going to see, many of the neural networks and decision tree and random forest algorithms actually are part of supervised learning. Examples of tasks that are very commonly done by supervised learning is estimation of or prediction of house prices, spam detection, cancer prediction, because they involve learning between pairs of inputs and outputs. Now, unsupervised learning is a form of learning in which we actually do not have labels. Actually, we do not have the output. So in unsupervised learning, we just have a set of inputs, and we would like to learn the structure from this set of data. So usually we would like to learn some type of hidden structure from the data, and these algorithms are mostly used for knowledge discovery. Unsupervised learning is a less well-defined problem, and there are no obvious error metrics just because we do not have labels. An example of supervised learning could be the way Google News clusters data, clusters news topics in order to send them on your phone. So in this case, it could be, let's say, performing a topic modeling in order to model different documents, different articles based on their similarity with each other. Finally, the last type of learning refers to reinforcement learning. Reinforcement learning, essentially, we can say that it is in the middle of supervised and unsupervised. Examples of reinforcement learning applications include self-driving cars, robot navigation, and game playing. And the important thing about this is that as part of reinforcement learning, the labels are not being provided from the beginning to the algorithm, but the labels are being learned as the algorithm proceeds throughout the task. So let's say if I'm performing robot navigation and my robot can go across 4 directions, I honestly do not know the labels of each of the 4 directions before I try them. I only know the label, whether this is a good direction or a bad direction, for example, after I have tried to experiment with this specific direction. So a little bit more detail into supervised learning and some general representation of algorithms and models. As we discussed, supervised learning learns a mapping between inputs to outputs. For the purposes of this class, we are going to denote inputs as vectors X, and usually these are referred to as our features. So if we have, let's say, a task of facial recognition, a set of inputs can be different shapes, can be measures that quantify shapes of the face. So for example, the size of the eyes, the size of the lips, of the nose, the distance between the eyes, the distance between the cheekbones, all these things. So these can be attributes that are relevant to the task of facial recognition, just because we know that different people have different face structure. And therefore, by quantifying their face structure as a set of input vectors, we can potentially recognize them. Now, the output, usually, if we have a supervised learning task that has, for example, that is most commonly used, usually it has one output. If we have the example of face recognition, it can have the output of the specific person that's being recognized. So the output can be denoted by scalar y. And in this case, as you can see, we have a set of samples D that are being formed by pairs of inputs and outputs. Again, the input is usually a D-dimensional vector that represents a set of attributes for each sample, and the output can be either a scalar or a vector, depending on the application. So the same set of data can be represented either as a set of pairs or as what we call a data matrix. So here, a data matrix X can represent the set of vectors from the inputs. So if we superimpose all the inputs, we can have a data matrix X. And this is usually a useful representation when we will deal with our regression algorithms. So in supervised learning, we would like to learn a function that that approximates the association between our input x and our output y. And this function f that approximates this association, the shape and the form of this function depends on the machine learning algorithm that we are using. For example, if we use a logistic regression, this function is just going to be a simple sigmoid function. If we use a neural network algorithm, this function is going to be a more complicated collection of other functions. And as part of supervised learning, as you have already guessed, we can do both classification and regression. By classification, we mean that we can classify a sample as part of a specific class. And in this case, we have a set of separate classes that are being represented by an algorithm. An example of classification would be facial recognition, where let's say we have 10 different users, and we would like to estimate which image corresponds to which user. On the other side, as part of a regression task, we have a continuous real valued output for which we would like to predict its value. An example of the regression task would be the example of temperature prediction that we mentioned as part of our previous discussion. Here we can see an example of classification task in which we would like to perform to classify between 3 different types of flowers, Setosa, versicolor, and virginica. We can see that these different flowers have different attributes when it comes to their shape and when it comes to their color. So one potential way to try to differentiate across these 3 types of flowers is to quantify the sepal length and width, as well as the petal length and width of these flowers. In this graph, on the right side of the screen, we can see combinations of our attributes, of the 4 attributes, for the data of interest. So across the diagonal line of these scatter plots, of these plots, we can see the histogram of each of the 4 attributes. Position 1,1 represents the histogram of the sepal length attribute for the data that we have. Position 2,2 represents the histogram of the sepal width, and so forth and so on. Now, the non-diagonal elements represent scatter plots. And by scatter plots, we mean 2D plots of different feature attributes. So plot 1,2 represents the sepal width on the x-axis and the sepal length on the y-axis. And with the color coding in this plot refers to the class to which each sample belongs to. So on that graph, the blue star-shaped points represent the virginica flower. The red circled points represent the Setosa flower, and the green diamond-shaped points represent the versicolor. So we can see here that different combinations of input features have different degrees of differentiation with respect to the 3 classes. We can see, for example, that in this graph that represents the combination of sepal length and petal width, we can have pretty good differentiation between our 3 classes. And by this exploratory data analysis, we can actually understand which features might be more informative for the task of interest. If we zoom into this graph, which represents the sepal length and petal width, we can see now again our training samples. And again, let me remind you that our training samples are the color-coded points on this 2D graph, the red, green, and blue colored points. And we also have a test sample. The test sample has no color, and we actually need to assign a weight to our test sample based on the data that we have. So based on the data that we have, again, we can learn multiple types of models. This is what machine learning is about. A specific type and very simple type of model that we have in machine learning is the k-nearest neighbor classifier. And this model is actually very intuitive and very simple. So what KNN does is that it assigns a sample, a test sample for which we do not have a label, to the most common class among its neighbors. We can see that for this test sample, most of its neighbors, most of its closest points belong to the red class. Therefore, it's very likely that this test sample belongs actually to the red class and can be assigned to the red color. Let's say now, though, that we have another test sample, like we denote in the screen, that is a little bit more ambiguous and actually lies between classes. So for this test sample, we can see that there are some neighbors that belong to the blue class and some neighbors that belong to the green class. In order to better capture this ambiguity, or this uncertainty, as we call it, we can actually introduce probabilities. So we can actually introduce the likelihood of this test sample belonging to the blue class and the likelihood of this test sample belonging to the green, as well as the likelihood of this test sample belonging to the white class. And actually, if we were to do a very short probability review here, let me remind everyone that if A is an event, P of A can be denoted as the probability of an event. And we also have the conditional probability. And the conditional probability is something that is very useful in machine learning because we usually condition on the data that we have. And if we have a supervised learning task, we condition on the labeled data that we have. An example from everyday life would be that we have data that today is humid and windy. What is the probability that we will have rain tomorrow? Now, if we were to translate this into our ambiguous test sample from our flower classification example, we would compute the probability of the test sample belonging to each of the three classes, conditioned on all the colored coded data that it has seen. And overall, this can be expressed in mathematical terms with this probability P of Y equals C given X and D. And let me walk you through this mathematical definition. So Y is the output class, essentially Y is the output. C is each of the different classes. In our case, we have three classes. So C can span between the red, the blue, and the green class. X, in this case, are the attributes of our test sample. So for this specific case, X would be the value of the petal width and sepal length for our test sample. And D represents the set of data for which we have labels. So in our case, D would represent the input pairs of all the color-coded data that we have in this graph. So the probability of Y equals C given X and D corresponds to the probability of a test sample belonging to class C given its attributes and the training set D. And usually this is called posterior probability. So we would actually make a decision about that if we found the most likely class for this test sample. We would calculate this posterior probability for each of the three classes and assign this test sample to the class that corresponds to this largest posterior probability. This uncertainty quantification is actually quite important in many applications, including a lot of biomedical applications. So an example, again, that we can that can help us better understand uncertainty. In this case, we provide a training set D that has data from two different classes, class A and class B. And we can see that these data have different forms, shapes, and colors. These data are labeled. So we know that all the data below class A have a label of class A, and all the data below class B have a label of class B. And finally, we have two test samples, S1 and S2. Each of these test samples, again, has a different shape and a different color. So the question here is, what is the probability of each test sample belonging to class A or class B, given the data that we have, given the training set D? So what we can see for test sample S1 is that S1 represents an oval shape with dark red color. We can see that there is an oval shape with lighter red color at class B. So it's very likely that sample S1 also belongs to class B. Now, so among these choices that we have, it's very likely that the probability of S1 belonging to class B, given our data D, is close to 1. In this case, we can say that it might be close to around 0.9. So this, the only two choices that actually have this correct are choices B and C. Now let's look for test sample S2. We know that test sample S2 has kind of a circular shape and is yellow. We can see that for class A, we have two oval shaped shapes with yellow color. And class B, again, we have another oval shaped shape with a red color, but this one actually has this hole in the middle, which very much is similar to test sample S2. So actually, there is not much real that we can infer from these two, because we have a similarly colored shape in class A that doesn't have exactly the same shape, just because it doesn't have the hole in the middle. But we also have a very similarly colored shape for class B that actually has this hole in the middle. So we can say that the probability of S2 belonging to class A is equal to the probability of S2 belonging to class B, which is equal to 0.5. So the correct choice here would be C. This example is here to demonstrate that we need to handle ambiguous cases in ways that might be more fit to the application that we have at hand. Probabilistically, having probabilistic ways might be one of the best ways in order to handle these ambiguous cases. And another thing for this example here is that if you noticed, the features or the attributes that can be used to represent our training set can be both categorical and continuous. So each shape can be represented by its color and its shape, which are categorical attributes, as well as by its size, which is a continuous attribute. Another now subcomponent of supervised learning is regression. So regression, as we discussed, is the task in which we would like to predict a continuous value based on a set of inputs. An example here would be predicting the price of a car based on its attributes. For example, its brand, its year, its mileage. In this case, if we have, let's say, a linear regression model or even a nonlinear regression model, we will have a function f that learns a linear or nonlinear association between the input and the output. So in the first line that we have this linear model, this function f is being represented by these weights w that assign that multiply each of the different attributes with a different value. These weights are being learned in order to associate in the most accurate extent as possible the input, which are the car attributes, with the output, which is the price of the car. Instead of having this linear association between input and output, we can also have non-linear associations, and we're going to see how we can quantify those as well. So moving a little bit forward into unsupervised learning, as we mentioned, unsupervised learning aims to discover structure in data, patterns, regularities, irregularities. And for this reason, because this is a more exploratory task in nature, there are no labels. So we just want to find associations between data samples. Specific types of unsupervised learning that exists include clustering, where essentially we would like to identify subpopulations in our data. A type of clustering could be if we are given different pictures of dogs, and we would like to identify which dogs are similar to each other. Another type of unsupervised learning could be dimensionality reduction, where we can project our data to a lower dimensional subspace. And finally, matrix completion, which refers to the task of data imputation in order to predict values of non-existing entries. Matrix completion is what your Netflix and all these applications do for us. So essentially, they have a matrix that is very sparse, and they're trying to complete these sparse entries in order to approximate our preferences. In this example here, you can see an example of clustering. In this case, let's say that we had a set of samples as shown on the left figure in the screen, and then on the right figure of the screen, we can see how these samples have been clustered into two different groups. This is an example of dimensionality reduction, where we have a three-dimensional space, and this three-dimensional space is being projected into a two-dimensional space. In this specific example, we have the algorithm that we call principal component analysis that we are going to discuss, but of course there are many different other types of dimensionality reduction algorithms. An application, a very exciting application of principal component analysis is the fact that via principal component analysis, we can identify eigenfaces, which means we can identify modular faces from a large facial recognition dataset. So this means that we can identify a generic structure of all the faces that have been seen by the algorithms, by the algorithm from our data. And based on this generic structure, we can decompose a new face using each of these substructures that have been learned. PCA can be also used for other applications such as MRI denoising, where essentially we can disentangle noisy dimensions versus non-noisy dimensions of our images. And here you can see an example of matrix completion, as we discussed with recommender systems, as well as a matrix completion example for image restoration, where essentially images, historical images, can be restored automatically by an algorithm that learns patterns and therefore can actually use the learned patterns in order to restore missing parts of these historical images. To sum up, what we discussed in this video was the definition of machine learning, several key components of learning, including the representation of an algorithm, the evaluation and optimization. We also discussed different types of learning, as well as some specific details and some examples of algorithms as far as supervised and unsupervised learning is concerned.